Hi, so in this video, I want to go over a method that we use to determine the concentrations of non-equilibrated systems once they reach equilibrium. So this is really helpful for just one, predicting like how a reaction is going to change given enough time to equilibrate, but then also, right, show us like what the final product will be, how much of our products we'll have, how much of our reactants we'll have once we do reach that equilibrated state. But so to begin, let's consider this reaction right here where I have hydrogen and iodine forming hydrogen iodide gas. And for this, let's just say that the equilibrium constant of concentrations is 50. Now let's say that I have a container that has initially in it just hydrogen iodide gas. So none of the hydrogen, none of the iodine, but that concentration of the HI is 0.5 molar. My first question here is the system at equilibrium, right? Have we reached that equilibrated state? Now, just initially, right off the bat, I can see, okay, I only have product here. I have no reactants. So no matter what, this is not equilibrated, right? Equilibrium requires some balance of products and reactants. And so the fact that there are no reactants initially in this mixture, that tells me that this is not at equilibrium. My second question then is, what will equilibrium look like? What will the concentration of hydrogen iodide be once that system has in fact equilibrated? So the way that we're going to approach this question is through the use of what are called ICE tables. Now, ICE here is short for initial change equilibrium. Sometimes I also refer to these as RICE tables. So we have like the reaction at the top of the table and then these three things. But these are used as an accounting method to keep track of the concentrations of our products and reactants before, during, and after a reaction, or really like once the system has reached equilibrium. So I've set up right here an ICE table for this same reaction, right? So I start with the reaction up at the top. I include the chemical formulas and the molar coefficients. It's not necessarily needed, but I also show the states of matter as well. And so I show that just as the balanced chemical equation would usually be written. On the side, you can see 3 rows labeled initial, change, and equilibrium. These rows are going to represent the amounts of our different reactants and products at those different times. So we'll begin by filling this in with the initial concentration of all of the chemicals that are in this problem. So recall that we were told that this container initially only has hydrogen iodide gas in it with a concentration of 0.5 molar. So I can fill that in the initial row. Under each chemical is its own column. So for hydrogen, for instance, there's no hydrogen in there, so we say its initial concentration is 0. Same for the iodine, right, 0, and then the hydrogen iodide, that will be listed as 0.5. It should be noted that when we use an ICE table, right, the amounts that go into here are always the molarity concentrations, unless we're working with, say, like a KP, and we can use the pressures in that case. But generally speaking, our ICE tables are going to have just the molarity concentrations as these different amounts. But so, right, this initial line just represents what we're starting with for our products and reactants. We can then continue this process by addressing the change line. The change in concentration for each of these products and reactants is dependent on kind of the molar coefficients and also which way the reaction is going. So for instance here, I'll just fill in the change line for each of these guys. I put this in terms of a variable x. So x just serves as a placeholder. We don't necessarily know just how much our different reactant amounts are going to change yet, but we do know that those changes are going to be proportional to one another dependent on what the molar coefficient is. So you'll see here that like for hydrogen iodide, it has 2x in its change variable, whereas hydrogen and iodine, they're just represented as a single x, and that's because of their molar coefficients in the balanced chemical equation. Now, additionally, you'll note that each of these changes has either a positive or negative sign to it. That depends on which way the reaction is going to shift in order to reach equilibrium. So we can be sure of the direction of change by calculating, say, Q or the reaction quotient and comparing that to our equilibrium constant. Or here, kind of like just a really simple way to know which way the reaction is going to shift. Because we have 0 initially of the hydrogen and the iodine, we have to add to those amounts, right? We have to add to the reactants in order for this reaction to reach equilibrium. We can't end up with like a negative amount of hydrogen or iodine here, so we're just going to add on the reactant side and thus subtract from the product side. But so my full change line can be seen below, where I have hydrogen and iodine as plus X, and then hydrogen iodide as minus 2X. Again, keep in mind the molar coefficients and keep in mind which way the reaction is shifting, if we're going to add to the products or add to the reactants, and kind of going based off of that. Now for our final row in the ICE table, that represents the equilibrium concentration. In essence, like our final concentration after we've changed our initial amount. And so the equilibrium concentration is determined as just the initial plus the change. So basically adding together those first two lines, we can find then the equilibrium concentration for each of our different chemicals. So for hydrogen, if we had 0 initially and we add X to that, then our equilibrium concentration should just be X. Same goes for the iodine. And then for the hydrogen iodide, because we started with 0.5 molar, we subtract from that 2X. And so our equilibrium concentration is 0.5 minus 2X, right? That will be our final amount of the hydrogen iodide. Now still, X here is a little bit of a mystery, right? As I mentioned before, we're just using that as a placeholder, but we can solve for X by using the equilibrium constant itself, right? So the equilibrium constant, we were told at the start of this problem, was 50. If we write out the expression for the equilibrium constant in terms of concentrations, and then we plug in our equilibrium concentrations from the ICE table, we can then kind of set up an equation in which we'll solve for X related to that Kc constant. And so that's what I've set up right here, where I say that Kc is equal to 50, which is equal to the concentration of Hi squared divided by the concentration of H2 and the concentration of I2, or in terms of all of these X's and things, right? You can see the expression just right there. Now, actually solving for X can be a little tricky. Sometimes it's just like simple algebra, but sometimes there are some tricks that we can use. So let's go ahead and solve for X. Again, setting up my Kc expression, and this time I've kind of simplified it down. I've combined some terms, but basically I have this algebraic equation where 50 is equal to, in parentheses here, 0.5 minus 2X. That is squared divided by X squared. Now it's kind of like a fun little math trick, right? Remember that when we have a fraction and the numerator is a square and the denominator is a square, we can just take the square root of the entire fraction and that will remove the square from both the numerator and the denominator. So that's to say, if I were to take the square root of both sides of this equation, I would get then the square root of 50 on the left side equal to 0.5 minus 2x divided by x, right? The squares on both the numerator and the denominator have disappeared. So this is just one of our like little algebraic tricks that we can use sometimes for this. This only works because both the numerator and the denominator were squared, as we see in this example. That won't be the case necessarily for every ICE table, but it works here and helps us make the math just like a little bit more simple here. So actually solving for this, right, I take the square root of 50 and I find that that's 7.07. Again, that's equal to this fraction that I now have set up of 0.5 minus 2x divided by x. I can then start kind of going through the steps algebraically, combining like terms, and eventually I should be able to solve for x as equal to 0.055. So right, this X value is again just a placeholder that we use in our ICE table to represent kind of how much change occurs to any one of our reactants. X is not necessarily our final concentration of anything in here, right? In order to know the real context of X, we want to go and plug that back into our ICE table, and then we can see in the equilibrium line, again, our final concentrations of all of our products and reactants, right? By using that X value that we solved from the Kc constant, we can then determine our equilibrium concentrations. So let's go ahead and do that, right? If I say that X is equal to this number 0.055, that means then that the concentration of hydrogen at equilibrium is 0.055. The same for the iodine, right? Because those were both, according to our ICE table, just X at equilibrium, we can just plug that X that we found right back in. For the hydrogen iodide though, right, the concentration is defined as 0.5 minus 2x. So in order to give us like a real number there, I'll plug 0.055 into that. and I should be left with 0.39 as our molarity concentration of hydrogen iodide. So right, again, this is how we use an ICE table or a RICE table to determine the equilibrium concentrations of our products and reactants in a non-equilibrated system once it reaches equilibrium. Right, this is a really helpful tool that we're going to be using as just like a simple accounting method and a way to keep track of kind of how our products and reactants change over a reaction. Let's look at one other example right here. So this time I want us to consider this reaction of carbon monoxide and water vapor producing carbon dioxide and hydrogen gas. This has a Kc constant of 0.578. And let's say initially I have a mixture of all of these gases. So not just like one gas and then seeing, how it changes. Here I have a gas mixture which is 0.200 molar in carbon monoxide, in water vapor, in carbon dioxide, and in hydrogen. Right, all of these concentrations are going to initially be the same. So here I want us to, again, think about how this reaction mixture will change because I'm going to guess here that this is not equilibrated. We're not told that this is at equilibrium. So the question then becomes, what will the concentration of, let's say, hydrogen be once this has reached equilibrium? So go ahead and pause. You're definitely going to need a few minutes to think through how this ICE table method kind of can be applied in this situation. But go ahead and try to set up an ICE table, set up your initial, change, and equilibrium concentrations, try to solve for X, and then determine what the H2 concentration will be at equilibrium. Pause, take a few minutes to do that, and then we'll come back together in just a little bit and walk through it. Okay, so hopefully you've taken a little bit of time to try to set things up how we did before, right? Just mimic that same process. This process will be used a lot throughout the entire quarter, and so you'll get really familiar with the ICE table method. That said, right, if you're confused about it at all right now, definitely take the time to really sit with it, ask me questions, and we can work through it together. Right? I really want to make sure that this concept is down clearly because we are going to be using it a lot throughout the term. But so that said, right, my final answer here for the concentration of H2 at equilibrium, I found to be B, or 0.173 molar. Let's discuss why this is. So I'll walk through my whole process right here, and we'll see another example of an ICE table being used to answer this question of our equilibrium concentrations from some maybe non-equilibrium beginnings. So to begin here, right, first thing that I'm going to do is just set up an ICE table. So again, my ICE table should look like the reaction at the top, and then ICE I write on the sides. Again, that's short for initial, change, and equilibrium. What I'm going to put into that ICE table then next are the initial concentrations of all of my products and reactants. Again, here they're all kind of conveniently just 0.200 molar. So for every single one of these, I'll write 0.200 as the initial line. Then following that up, I want to start looking at the change line. Now I know that my change variable X is going to be multiplied by whatever our molar coefficient is for that chemical. Each of these just have a molar coefficient of 1, so these are all going to be changing by 1x. Now here, kind of the tricky thing is determining which way the reaction is going to go, right? Am I going to be adding to the reactants? Am I going to be adding to the products? And before, in our previous example, it was really easy to know that just based off of the fact that one of our reactants, or both of our reactants actually, had 0 initially. We can only add to 0, so anytime we see an initial of 0, we know that we need to add to that side of the reaction. Here though, because we're starting with some reactants and we're starting with some products, it's not totally obvious which side is going to lose and which side is going to gain. What we can do though is take a look at the Q, right, the reaction quotient, and compare that to K. So recall that Q is basically just the K constant expression, but just not necessarily at equilibrium. So in this case, I would calculate my reaction quotient as the concentration of the products divided by the concentrations of the reactants, just using these initial, maybe non-equilibrium amounts. And so doing that, I end up with a reaction quotient of just 1, right? If I plug in all of my concentrations right here, they even each other out and they reach 1. Now what I want us to consider is how Q compares to K. So our K constant we're given at the top as 0.578. We can see that Q is a little bit larger than that. What that implies is that we have more products than we actually want, right? In order to reach equilibrium, we're going to need a smaller numerator and a larger denominator. So that means then that, right, the reactants themselves should increase in amount and the products will decrease. That's to say that we'll have positive X on the reactant side and negative X on the product side. So again, if we have a 0 initially as any of our products and reactants, we can use that to determine which way the reaction is going because we have to add to 0. But if we have all non-zero values initially, then we need to calculate Q, compare that to K, and decide then which way the reaction will shift, right? Which side it will then move towards. In this case, we're moving towards the reactant, so we should end up with larger final concentrations for our reactants and smaller final concentrations for our products. And so now that I've kind of decided which way X is going to change, I have then in the final row right here my equilibrium concentrations of each of my different reactants and products. This is still just in terms of X, but it is like 0.200 plus X for carbon monoxide and water vapor, and then 0.200 minus X for carbon dioxide and hydrogen. So again, just combining the initial plus the change line, that should give you your equilibrium line. Now finally, I want to solve for X itself. I'm going to solve that using my equilibrium constant and the expression that goes with it. So the equilibrium constant again is 0.578. This should be equal to the concentration of the CO2 times the concentration of H2 divided by the concentration of CO and the concentration of H2O. Or as I've kind of plugged them all in right here, basically I have 0.200 minus X squared. That's not squared because like any of these have a molar coefficient of 2, but it's because, right, when we take our concentration of CO2 and we multiply that by the concentration of H2 at equilibrium, those are the same numbers. So the same number multiplied by itself is just that number squared. So we've got 0.200 minus X squared in the numerator, 0.200 plus X squared in the denominator. Again, doing my quick little like square root of both sides trick that we saw before, I can take the square root of 0.578 and I get 0.760. That's equal to now 0.200 minus X divided by 0.200 plus X. So here I just took the square root on both sides of my equation. And then again here I'm going to try to like just get through the algebra. What I want to do is eventually isolate X. So I'm going to say multiply both sides by the denominator of that fraction. And then I'll start combining like terms, putting my X's together and putting my non-X's together, and that brings me to this point where I have 1.760x equal to 0.048. I can then solve for x as 0.027. So again, this X value is not necessarily my final answer here of the concentration of H2 at equilibrium, but it does play a role in that final concentration. If we look back at our ICE table, right, we can plug X back into the ICE table, specifically in the equilibrium line, and give us then our final amounts for all of our different products and reactants. So plugging X back in here, we now have for, say, the carbon monoxide and the H2O, not just 0.200, but 0.200 plus this value for X that we found. Or for the CO2 and the H2, right, we have 0.200 minus this value for X that we found. So putting all of that together, I have 0.227 as the concentration for both CO and H2O, and then 0.173 as the concentration for both CO2 and H2. So again, this is an example of how we can use an ICE table to determine our equilibrium concentrations of not just one of our products, right, but really all of our products and all of our reactants. The ICE table is a super helpful method just for keeping track of all of the different things that go on in a chemical reaction. But please let me know if you have any questions on this, and I'm always happy to help.